Hi, good morning. I'm Daniel Rodwell, as I was introduced, the manager of the HPC, data storage services team at NCI. What I'll talk about today is a bit of a run through about, very quickly, about what NCI is and our HPC system and some of the file systems we've got at NCI. The main part of the talk would be around the Lustre HSM project that I've been running, however. So what is NCI? NCI is a collaboration between one of our research-intensive universities and 3 of our large government science organisations. We're also partnered with a number of other research-intensive universities in Australia. We're located in Canberra, in Australia, which is a fairly long way from here, at our national university, ANU. So you might see on a few slides that we're often referred to as ANU or NCI. So who are our users and what is the research community that we support with our system? Is a large percentage of our activities are around climate science and climate modelling, then followed by astronomy and our geosciences. That's largely a function of the organisations that we're partnered with and their researchers. So who uses NCI? We've got around about 3,000 active users in 600 projects. We add about 10 extra users a week, and they come from a range of backgrounds. Some of them are first-time HPC users, and some of them have been doing this for years and years. Some use commercial packages, others write their own code. And this is some of the areas that they work in. As you can see, there's a large percentage of the allocation on the machine is around the earth sciences. So what is the machine at NCI? It's a system called Reims, which is named after the Japanese Shinto god of thunder and storms. And this is what the machine looks like. It's a 57,000 core cluster and is held together with FDR InfiniBand. The short or the scratch file system there is 7.6 petabytes on DDN storage. I'll talk a bit more about that in a minute. We were ranked 24th in the top 500 when we went live with the system. And we run CentOS 6.5 with a PBS Pro scheduler that's been fairly customised. The storage systems at NCI. We run around about 22 petabytes of Lustre at the site. And they're broken down into these systems. So we have our Reims Lustre, our HPC-facing systems. File systems. And the biggest there is 7.6 petabytes, which is usually around about 150 gigabytes a second on an IOR run, depending on the configuration that it's set up for at the time. That runs Lustre 242, plus some custom patches that we have in place, and that's directly through DDN. Next week, we'll upgrade to Lustre 253 on the 1st of October during a major maintenance event. Hopefully that goes well. We also run GData 1 and GData 2. They're called GData for global data, and the number just is an incrementing number. 7.4 petabytes on our first GData 1 system. We've been running that for around about 18 months now. And that's a SGI-based system with running Lustre 2311 or Intel Enterprise Edition Lustre version 1. We'll keep that on the version of Intel Lustre where it is for the moment because of some of the stability things that we're seeing there. It's very stable and we're seeing very strong demand for that file system. The main part that I'll be talking about later in the presentation is around GData 2, which is the persistent data store that I've been building over the last 4 months. Its targeted size is 6.75 petabytes, and that's through adding an additional DDN SFA 12K. We've benchmarked around using 2 SFA 12Ks at 46 gigabytes a second. That was on Lustre 2311 on those initial benchmark runs, but we're currently rebuilding this file system as 253 on the recently released Intel Lustre 2. Other file systems that we run on site is our long-running mass data file system, which is a migrating CXFS DMF system with a 1 petabyte of cache in front of about 12 petabytes of tape. And we've also looking at using Ceph. We have 2 Ceph deployments. One of them is currently in production and the other one's about to go into production. There's a fairly reasonable allocation there at 1 petabyte, and that's something that we're spending more time looking into. And a bit of a layout on how our environments fit together here in a very simple diagram. Now onto the main part, around Lustre HSM. So a bit of history first. Why do we use Lustre HSM? Our previous systems, we had a 900 terabyte in Lustre 1.8 install, the original G-data. That was hooked up to our previous generation HPC system. We also had a CXFS dual-stated file system there of about 1.4 petabytes. And that was backed by our 2 LTO5 tape libraries. But some of the things that we looked at in moving from our previous generation supercomputer onto Ryzen at 1.2 petaflops is that we needed to be able to both grow the data sets that we were holding on site, and that was a strong indication that we got from our researchers that were using the system, and we had some scalability concerns around how these file systems would actually handle a petaflop and beyond workload. Some of these file systems that we're building today will actually span into our next generation HPC system. So what were some of the requirements? Was that it had to be high performance because this was a HPC connected workload. It wasn't primarily servicing HPC, but there's a fairly significant compute resource also talking to this thing. And we also needed a large storage capacity. That was given, we determined that through some of the research data collection sets that we wanted to bring on site, so we'd have them in close proximity to the compute. And we also, this was designed to be a persistent data store, not something that would be like a scratch file system, but something that we would want to be able to back up essentially in a very broad term. In other words, have something beyond a single copy of data on disk. And we wanted something that was also modular, that we could build partly now and be able to scale that out should our storage requirements change. We also knew that we'd need at least 20 gigabytes a second to service this kind of workload. With these kind of numbers, it started to send us in a particular direction around what kind of file system that we would need, and Lustre looked like a pretty good fit. As part of the global data theme, we wanted to make sure that this file system these file systems would be available across all of NCI's facility. So on our cloud systems, our VMware installation, and HPC. So a bit of an overview of what they look like is G-Data 1 is 7.4 petabytes. Currently we're sitting at 4.2 petabytes used with 150 million inodes on that. G-Data 2, in the process of going live with that. Our estimates would be that there'd be 300 to 400 million inodes per G-Data and possibly looking at 800 million inodes, possibly 1 billion inodes across these 2 file systems. So the idea of a traditional backup started to become something that didn't look very favourable because of the deep traversal and directory scans. Who knows how long that would actually take? And what would a backup event as such look like? This is not something that you'd run every night and take a couple of hours to run. So the actual calculation of the differences, the deltas in the backup events, they may actually take days or weeks to determine. So, and the other thing that we were concerned about there would be the impact on the MDS, that how much of the MDS's resources would be spent on trying to figure out what to back up rather than actually delivering a usable file system to our users. So the HSM as a backup come to the front as a possible solution. Because with the Lustre changelogs enabled, the MDS knows which files are being accessed and what's changing on there. So you don't need to do these deep traversals. And the other thing is when you've got the correctly set policies in place, the backup itself is essentially always occurring. You end up with this light persistent load and the data is being sent to the tape tier as it's being created or modified, rather in large incremental batches. So what are our building blocks for our G-Data 1 file system? The G-Data 1 file system is probably worth pointing out up front, is probably not the most optimal design, and that comes from reusing some of our existing storage arrays that we had on site. It's running CentOS 6.4. And one of the things that we've learnt also through this is that using the Mellanox OFED will also deliver quite a performance gain, and it's currently on Lustre 2311. The storage arrays are based off SGI's infinite storage block storage arrays, which are essentially NetApp E-series underneath. We've got 12 of these infinite storage arrays forming the GData1 file system. As you can tell, there's some slight differences with this, which does result in some mild hotspotting within the file system performance. However, it's stable and delivering well above 20 gigabytes a second. GData2 has been designed with a lot more intent and is a far more consistent file system. We've also increased the performance of our MDSs and our OSSs from our experience on GData1. The building blocks for GData2 are 3 SFA 12K 40s with an IB backend on those. And for the MDTs, they're shared between GData1 and GData2 on a IS5000, another NetApp style array. What you'll notice between GData1 and GData2 is a scale up of the number of disks for the MDT. That's partly to scale up the small file performance that we've seen. One thing that we didn't anticipate with building this as a persistent data store was the amount of 4K IOPS that we were seeing on this. We thought it would be a lot of large file transactions going on. That's certainly not the case. We're seeing a lot of very, very intermittent data access, and in fact, some people are directly running their jobs against these file systems from the HPC side. The layout of the IB and fibre channel fabric. I'll refer to this diagram in a few slides, but this is to give you an idea of how this is all stitched together. The file systems themselves are presented using FDR IB, and what we've also done is span the sites involved here. So what you'll notice is most of the servers and the install here is sitting in the NCI data centre, but we do have a presence in our older data centre at Leonard Huxley. So one of the things about designing this HSM, we had to think around how we'd configure this and what it might look like. So we wanted to use the HSM as essentially a backup rather than a traditional migrating tier. So all of the Lustre objects would always be dual stated, as in they'll always be on the primary disk and copied to the HSM tape tier. But we also wanted the tape backend to be able to be copied or dual sited, so it could be copied on both data centres. And that was protect against a site failure, fire, flood, and to offer some tape level protection based off our experience with LTO5. We have a fair few unpredictable tape faults on LTO5 as it is today. The HSM stack, pretty straightforward. The main part being here that we're using DMF as our tape tier and using DMF copy tool, which you'll note is version 1.0. We expect that there might be some interesting things happen there. And we're also using our same SpectraLogic T950 tape libraries, but we've purchased a few additional libraries, running IBM 3592 tape, or commonly known as Jaguar. I'll talk about that in a few more slides as well. So what we wanted was a dedicated DMF instance. That was partly to protect our existing mass data file system, so that if there was a failure in the DMF side of things, or we overwhelmed DMF, we wouldn't take out our mass data file system. We don't know how this is going to behave or what some of the problems will be, so we wanted to make sure that the failure domains were contained. What we've also used, as you'll notice the pictures reused here, is our previous generation OSSs from our original GData file system. We've repurposed those as Lustre DMF data movers. They don't have the high performance requirements of what our modern OSSs will need, but they're well and truly adequate to drive the tape workload. So, the interesting part, the challenges in our experience so far. So the first challenge we thought that we'll have to solve is around our tape libraries. So we had a look at our existing tape system. It's DMF, mass data, 1 petabyte of cache, 12 petabytes of tape. But it was a migrating file system. Primarily, the intended state for it is to end in an offline state on tape, dual site copied. not on disk. So what that meant is there's a very large mix of reads, recall events and writes, which means that there's a lot of tape movement going on, a lot of load cycles on the drives. And that's, for the SpectraLogic T950s, that means that there's one robotics unit per library. So what we've got there is a large number of drives. We've got 54 LTO5 drives, but they're LTO5. They're 140 megabytes a second when things go well. We've got a large number of LTO5 tapes, but we're actually almost at capacity as well there. So we also had a look at the anticipated Lustre HSM workload to see what we thought the HSM would look like. We knew that we wanted to be dual stated, so it would be primarily online and dual site. So what that would actually mean is that we would be primarily a write-based workload. There would be very, very few recalls. They would only be typically occurring in a recovery event. That would be a user's deleted their files, or there'd be some sort of disaster that occurred. We knew that it'd have to support very, very high performance file systems. And we wanted to be able to grow this out to our next generation GData, GData 3, which we're estimating may be in the 90 gigabytes a second range. We also knew that because of this, we'd have large streaming writes. So we needed actually a fairly high individual tape drive performance rate. And when we actually turn on a full HSM enabled copy between Lustre and DMF tier, this will likely monopolise the tape library for days or weeks at a time. It could be weeks writing that initial 1 to 2, 3 petabytes of data out to tape. So the answer to this was purchase some more tape libraries. By purchasing more tape libraries, we increased the number of robotics units that we had so we could handle more tape movements per hour. We again used the SpectraLogic T950s for this, but instead have used the IBM 3592 or Jaguar format for that. We have fewer but much faster, larger capacity drives, which isn't a problem because we will be write focused. There won't be recall events interrupting the loaded tapes. So what we're starting off with is 6 of these drives. TS1140 is pretty much at the end of it. It's still current, but it's anticipated there'll be a new generation coming out very soon. And that's where we'll upgrade to whatever the latest generation is. I'm guessing it'll be called TS1150, and which gives you the ability to upgrade or up-format the existing media. We think it'll be well suited for a Lustre HSM workload. And it means that Lustre's HSM activities won't interrupt our existing performance on mass data. The second challenge, Robinhood. So we had a look around at what I could find about Robinhood, and one of the things that I had a really hard time determining was how big should I make this thing? What's the database performance going to look like, and what should I tune? And that's partly because Lustre HSM is a very new thing. It's in its current state with 2.5. As we've heard, there's a lot of sites that are thinking about moving to it, but very few that have already got it in production. So I thought, okay, let's go on a fact-finding mission and see what we can determine here. So one of the ideas that we thought is, well, for GData 2, the workload we anticipate will be the same as what it is on GData 1. Most users won't be able to tell the difference between whether they're on GData 1 or GData 2 in terms of performance. So we configured and enabled the change logs as they were under Lustre 2311 on GData 1 when the file system was mostly idle. And then we observed the performance impact over a number of weeks. We think that it's around about a 5% hit that you take on turning that on. We then also looked at the change logs that were being produced by the MDS and had a bit of a count through of how many entries were being created per hour on average per every 24 hours. And there's a very, very rough guide. Thought, well, that's possibly the number of database insertions that we'll need to handle per hour. These are ballpark figures. But the thing that we also considered was that irrespective, if everything works perfectly, that the MDS and MDT performance could be a limiting factor here. One of the other things in playing around with determining what was an ideal Robinhood resource allocation was varying the database storage types. So we also looked at putting that on a 4-disk RAID 10 internal to one of the Robinhood servers and scaled that out onto 15K SAS and then out onto SSD and observed the change log processing rate on those. So the hardware that we actually have went with for using for Robinhood is our server hardware. We've repurposed two servers that we had on site already, a pair of Sandy Bridge Xeon Fujitsu RX 300s, and each of them have 128 gig of RAM. The main thing that we were concerned about there was the amount of RAM, with the idea that we wanted to keep as much of the database in memory as possible to avoid going out to disk. But for a test that we had a unique opportunity come up to do a test. And that was an evaluation system on loan from NetApp, their EF550, which is an all-flash array. And this product is supposed to support 450,000 IOPS sustain. And this was very good for doing a test like this, because what it allowed us to do was essentially have uncapped IOPS. It was remove the actual back-end storage as being a limiting factor at all. So we benchmarked that. This was hooked up using 10 gig iSCSI. We used 6 out of the 8 host ports on the array and benchmarked that up to 320,000 4K IOPS. The limitation that we hit there was essentially the CPU was maxed out in the RX 300. So what we went with in terms of our storage for our database in production, given that this is MySQL and we can easily relocate the database files should we need to scale up the performance, is using our second IS5000 at our second data center. It hosts a number of other applications, and what we've set up there is around 20 15K SAS disks for that. We think that it'll give us around about 4,000 read IOPS, 2,000 write IOPS. Not much in terms of when you compare it to a single SSD, but it seems to be adequate for what we need on this. 1.9 terabytes in size, probably far too large for what we need, so we'll short stroke the drives there. Thinking about the database and how it sits on that is that we'll optimize that for 4K I/O and tune for transactional rather than streaming or capacity requirements. Our 150 million inodes on GData1 on the initial Robinhood scan, that was a 99 gigabyte MySQL database. We actually managed to get that to fit in memory quite easily on the 128 gig in the RX 300s. That's something that we're trying to keep in mind. It may be worthwhile increasing the amount of memory inside those Robinhood servers. And one of the things we also wanted to do was make sure that we could potentially tune MySQL to try to get the indexes improved. We're also using 2 of these Robinhood servers, so we will have them as a HA pair, but 1 active per GData file system. Another interesting challenge we hit, challenge number 3, was a Lustre bug. This one hit us as a bit of a surprise. This happened while we were in production. We were running our initial scan, that completed. We then went on to handling the deltas and updating Robinhood as required. So we hit LU5405 and with very similar conditions reported in the bug at almost the same time as that bug was opened. Quick recap of what's in that bug is that as the changelog grows, the MDS spends so much time trying to figure out where to insert the new entries into it that it spends most of its time processing the changelog and not servicing requests as it should as an MDS. The active MDS will eventually become overwhelmed, and you'll see this with an incredibly high load average and the file system largely unresponsive. That happened in production. Thankfully, it was during business hours and we noticed, and so currently we've got that disabled until we apply the fix for it. The other challenge that we come across was around on the DMF side, which is one that I initially didn't predict, but when we had a look at how the copy tool works, it indicated that we need to think about this fairly clearly. DMF uses an intermediate XFS file system in front of the tape tier. And that's partly to provide this a pool of inodes acting as a pointer. So a translation between a Lustre object and a DMF BFID. It also serves as a cache file system, which I'll explain in a minute. But it allows you to have this browsable, there's a spelling mistake in my slide, I apologise, a browsable shadow file system as you'd see in Lustre. So what the screenshot is showing is what you'd typically see as a file name that you'd have on Lustre and what that translates to in the DMF XFS file system. As you can see, it's binning, having a binned directory approach here, which results in one inode, or one Lustre object not translating to one inode inside DMF. The number of inodes that we have to handle inside the XFS DMF file system will be quite substantial. So that brings me on to the next slide. Normally the DMF copy tool will move the data directly from the Lustre file system to the tape tier. So the actual data itself does not sit inside this XFS file system, just the creation of a pointer. However, we need to be able to accommodate a disaster recovery situation where Lustre might not be in a viable state. So we need to be able to get this data back should something go very wrong. We also needed sufficient capacity in the cache to be able to recall the data should something also not go well. So we need to be able to handle in that cache at least the largest file within the file system, and we need to be able to perform tape maintenance. So this is DMF related tape maintenance, not specifically related to Lustre. One of the things that we also needed to accommodate was the high IOPS required to do an XFS dump of this intermediate file system. This is because it's acting as essentially a bucket of pointers. If you lose this XFS file system, the information you have on tape becomes somewhat problematic to access. So what we're looking there is a need to be able to do a weekly XFS dump on this. The alternative would be rescanning and doing an initial HSM copy again. So it's not a critical requirement, but it's something that you definitely want to think about. So again, we went with a rough guide around how many disks that we'd need to do this and the number of inodes and how long an XFS dump would take. So we're allocating around 80 15K SAS disks to service that. Again, it's not really around a high capacity requirement, it's around the number of IOPS that we need to service there. The other thing that we looked at was to perform this tape maintenance. So if you look at TS1140 or JC media, it's 4 terabytes native, 8 terabytes with a 2:1 compression on it. A guess at the next generation, bit of a look around at what the rumours are on the web, and we think that it'll be in the 8 to 10 terabytes per tape, maybe 2:1 compression at 20 terabytes. So keeping that in mind, we need to be able to accommodate that. So the capacity involved here will be able to service it. The other thing that we wanted to think about was our disaster recovery design, so that the data would be recoverable after a primary site incident. So if we had a total loss at the NCI data centre, we would have a lot of problems, but we need to be able to recover the data, or it's certainly a nice to have. If we lost the primary site, we wouldn't have any HPC system to use the data. And if you wanted to restore this using a traditional notion of a restoration, where would you actually restore 14 petabytes to if you've lost your HPC centre? Still, it's something that we wanted to have. And that we'd be able to, so the recovery would not be a high performance requirement, but we'd want to be able to get data back, even if it was only a few terabytes at a time. So we've come up with a cross-site design, locating our DMF, the DMF file system and the Robin Hood database at our second site. We had an existing 8 gig fibre channel fabric that was spanned between the sites, and we also have a Mellanox Metro X 6100 spanning both of those sites, which gives you essentially 6 QDR links. So we could actually be able to recover this data and span some of the workload involved here. We positioned 3 of the 6 data movers at each site, and one of the T950s with the TS media in each site. So having a look at how we'd handle a failure at one of the sites. So if we lost the second site, which is primarily around the DMF install and the second tape library, this wouldn't be too much of a problem. Lustre wouldn't be affected, but Robin Hood would become unavailable, and DMF would also become unavailable because that's where the IS5000 with the database and the inodes are sitting. But our primary file systems won't be affected. We'll have a backlog of work that needs to be processed into the HSM, but the disk won't be affected and our users won't notice. What happens if we lost the whole HSM componentry? Again, the same thing. The HSM tier won't be available. All of the data will be dual stated, so it's both on tape and online. So all of the online objects will be still available on the primary file system. And should we lose the primary site, obviously the disk front ends, Lustre will be offline, and the tape library on our primary site may be offline. But what we'll be left with is our dual-sited tape copy in Leonard Huxley, a couple of servers to access that, and our DMF instance and the DMF file systems in between. That'll allow us to access that data and recover a small amount at a time. But it's sufficient to be able to acknowledge to our users, should something occur on our primary site, that their data is safe, it's secure, and we can recover it. But it may be a very slow process. So you're pretty sad, but it's not a fatal condition. The rollout plan is that we'll build GData 2 on Lustre 252, which is happening right now. Our existing GData 1 will upgrade that early next year, once we've proven GData 2 is working correctly with full HSM. So we'll build the GData 2 file system now, enable and tune the changelog configs for Robinhood. We'll build the Robinhood environment, then roll out the DMF components. We'll play around with some policies there to make sure that we've got that right, and then enable a full policy-driven HSM. Hopefully that'll happen this year. The reason why we're rolling that out in a phased approach is to simplify the troubleshooting, is that rolling this out in one big hit, if we encounter a problem, it may take a very long time to try to figure out where that is, and we need to be able to bring this file system online today to accommodate our increasing data growth. Any questions?
The way I understood, the HSM will require extra copy of the data because of data replication. So have you looked at the impact of this extra replication on the performance of application?
So that's a really good question. What our preferred design is that all of the applications that are actively executing on the HPC system, they should be doing that against our /short file system, our Scratch file system. So the intent is that for optimal performance, that users should stage that data into /short rather than using the GData file systems. They're really there as for persistent data stores and reference data sets. So if you were chasing absolute outright performance, we'd usually encourage our users to stage that data. However, what we have seen is that users are using GData 1 for active jobs. This is partly because some of our users they're quite happy with the performance that it's offering today. In fact, GData 1 has much higher performance than what our previous generation Scratch file system did on our previous supercomputer. So where we have concerns raised about the performance, yeah, we encourage them to migrate their data in.
Okay, thank you.
So do you intend to test disaster recovery before going to production? Because the metadata, the namespace in DMF might not be up to date, and you might need to rely on the policy engine to restore all the rename, the ownership change, and so on, to be able to restore.
Yep, that's a really good question as well. Definitely. Part of the advantage that we have here is that we've got our existing data on GData 1, and we're building GData 2 as this new file system. So it gives us the ability and that opportunity to test without impacting users. We don't have to upgrade an existing file system. So we'll prove this on GData 2 before we go live with it. And once we're satisfied with it, we can then do an upgrade on GData 1 and bring that up. It's a good approach that's sort of low risk, and it doesn't impact on our users. But definitely a good part of it about testing DMF as well.
You mentioned that you're using the Ceph file system. do you have any performance numbers there to share with us, or is it not configured for that?
Not performance, it's not really been configured for outright performance. That's something I'd like to give an update on in the future. We've only recently went live with it in production, and it's to service our cloud environment directly. It's something that we haven't really provisioned for high performance or sort of a global file system. But it's a bit of a learning experience along the way, and we're definitely looking at how that greater Ceph deployment fits in our future at NCI. Thank you.